now we add one predictor variable to our model. So if in the causal model we had the constant variable, or sorry, the constant, not the variable, an unknown variable, and now we add a variable of interest that we are measuring. So that becomes a more interesting causal model. Now, typically, this C is not going to be there. This is my my proposal, but you won't see these in typical models. And sometimes the U is presented and sometimes is ignored. So this could be the simplest causal model, if you like. Now, in terms of the linear model, the most common equation would be this, which is y equals beta 0 plus beta 1 times x plus epsilon. And epsilon is distributed normally with mean of 0 and standard deviation sigma. But remember, I prefer this different notation, which gives the probability distribution directly to the dependent variable or outcome variable. And we say that y is a random variable that follows a normal distribution. The mean of that distribution is gamma, and the standard deviation of that distribution is sigma. And then we say that gamma is beta 0 plus beta 1 times x. So this is the most simple linear model in which one variable is used as predictor, which this variable x is used as predictor of variable, the outcome variable y. Okay, in terms of model, graphically, well, we've got variable y, that is the outcome variable, variable x, which is the predictor variable, and now we have a line, and the name linear model comes from this blue line that we use to fit the data. Now that blue line is generated by the equation beta 0, which is the value of the y-axis that corresponds to an x of 0. So here the value x has values 0 to, I don't know, let's say 200, and so in the y-axis the value of y that corresponds to the 0 of x, that's beta 0, or is called in this case the intercept. And then the slope is given by the number of units of increase in y as a function of the increase of 1 unit in x. So for example, if beta 1 equals 0.5, it means that when x goes from, let's say, 1 to 2, then y will increase 0.5 points. If x goes from 10 to 20, then y will increase 0.5 times 10, or 5 points. And the value we expect for y then is given by this blue line and infinite number of normal distributions with mean in the values indicated by the blue line. Okay, so for example, if x is here, for the value of x, and we expect that values of y are centered around this mean here, but we expect values close to the mean, very likely for one side and to the other side of y, and values further away are very unlikely. And same here, if the x value is here, and the expected value of y is this one. And remember, how do we calculate this? Well, beta 0 plus beta 1 times x. And that will give us exactly that point. And that's the mean of the expected value for y. But values are there normally distributed, so we expect values that are close to the mean to be likely, and far from the mean less likely. So model fitted to the data is, well, so these values come from the data. This is the traditional way of estimating. So the blue line comes from beta 0 and beta 1, which are estimated, and the beta 0 and beta 1 will be the values that generate a line that minimizes the distance between the points and the line, or that maximizes the probabilities of obtaining these individual observations. So let's say if we do a line like this, let's say the beta 0 is here, and then the beta 1 indicates that the line goes like this, and then we will have some we expect values that are normally distributed around there. Sorry for the my normal distributions are not very nice, but look at this. The actual values are very far from the center, the mean of these normal distributions. So in these normal distributions, those white dots, which are the observed values, are very unlikely. So we don't want the values to be unlikely in order when we fit the model to the data. We want the models to be very likely, as much as to have the highest possible probability. So when we do the estimate, when we fit the model to the data, we try to come up with the best line that in a way in which the values are probable, quite as highly probable as possible. And obviously we don't do that. We don't calculate the beta 0 and beta 1 that best fits the data. We've got the software that will do that for us, but we need to understand what it means and what that software is doing.